good afternoon and welcome to today's webinar titled Integrating 2D EM Simulation into Your Design Workflow. My name is Arvind Krishnan and I will be your host today. On behalf of EMWorks, I welcome you all for today's webinar. Thank you. I'm going to start with a very brief introduction about EMWorks 2D. Next, we will go through what is the motivation for using such a product. After that, I'm going to be showing you live demonstration of the product using 3 different examples. Then we shall recap what we saw, and finally, we will have time for some Q&A session. EMWorks 2D is a new product released by EMWorks or Electromagnetic Works. It's a product that is completely embedded inside SOLIDWORKS, and it can perform quick and accurate 2D EM simulations. In the first release of the product, we have both electrostatic and magnetostatic simulations. Both planar geometries as well as axisymmetric 2D geometries can be simulated using EMWorks 2D. In the next slide, we'll take a look at the motivation for using such a product. Let us now look at the motivation for using EMWorks 2D. Imagine that you are a machine designer and you would like to design a linear actuator for your machine slide. So what would be your natural course of action? You're going to think of an idea of an actuator and you're going to quickly draw the actuator either as a part or an assembly or a concept or a sketch in SOLIDWORKS. Most likely, if you're a SOLIDWORKS user, you're going to do a 3D design of this linear actuator. What happens after you do the design? Are you sure it is going to work? This is where EMWorks 2D comes into play. EMWorks 2D can quickly take your concept and do a quick 2D EM simulation. Till you can perfect your data, you can continue doing the EM simulation. And once the simulation is complete, you can then take the model and do a full 3D simulation in EMS for SOLIDWORKS. Next, we'll be looking at live demonstration of the EMWorks 2D product. In this session, I will be showing you a demonstration of a linear actuator, something similar to what we discussed in the previous slide. I'll be showing you a demonstration of a Halbach array, which is actually the first one we'll be starting with. And finally, we will show you a demonstration of a 3-phase cable. Now in the Halbach array, the objective is really to understand the magnetic flux distribution due to the Halbach array and also understand the force acting on a steel plate due to this Halbach array. In a linear actuator, the objective is to understand the force acting on the armature. And finally, in a 3-phase cable, we will understand how effective is our insulator that surrounds these copper conductors when you apply, say, a 3-phase voltage to the copper conductors. Now, let us go straight into the product and look at these demonstrations. Suppose you have a Halbach array as shown here, and there is a steel plate in the bottom which is at a particular distance from the Halbach array, and you would like to find out what's the force acting on the steel plate. One can resort to a full 3D simulation, but it is much faster to understand the forces by doing a quick 2D simulation right inside SOLIDWORKS. So the first step in doing the 2D simulation is to go to the EMWorks 2D Manager tab, and here one can go ahead and run the 3D to 2D operation. We can select a plane. In this case, I select the front plane and I say OK. So the program automatically creates all the necessary surfaces to do a 2D simulation, as you see here. Okay. So if you have a 3D geometry, it's extremely easy using EMWorks to get an equivalent 2D surfaces to do a 2D simulation. So once you have this, you can see the various surfaces that form the part of these various components. The first step is to create a study. So we create a study. And before we create a study, one can go ahead and do a coordinate system. So let's go ahead and do that. I'm going to insert reference geometry, a coordinate system. So we can do a coordinate system where the XY plane lies in the plane of the surface. So here you have a coordinate system. So once we have a coordinate system, we create a study. In this case, we're going to do a magnetostatic study. And then we select the coordinate system that is going to be used for this study. After defining the study, we have to now define the materials for the various components. So let's look them one by one. So if I go ahead and select all the magnets and I go ahead and apply materials, EMS 2D comes with the same standard material library, and you can go ahead and select your magnet. So in this case we are using N42. Then you can select the steel and I go ahead apply material, and from the list of ferromagnetic material I select mild steel, and finally the air geometry, you apply material, and then from the EMS material tree we select the air. So once the material is applied, we can now go ahead and define the direction of each of the magnets in the Hallbach array. So it's easy to select the magnet from the screen. You go ahead and apply direction, the coercivity direction. We need to select the coordinate system, and this is in the Y direction with respect to the coordinate system, and you can decide to show so you can see using an arrow one can see the direction of the magnet. So let's go ahead and quickly define the rest of the magnets. So we select the same coordinate system, but this is now in the positive X direction. And as you see here, so the third magnet is in the negative Y direction. Let's see the preview, and the fourth magnet is in the negative X direction. And the last and the final magnet is in the positive Y direction. Thus, the Hallbach array is easily defined using EMWorks 2D. Now, once we define all the materials, we have to request the program to compute the force acting on the steel plate. So here we request EMS to compute the force acting on the steel plate, and that's all. And what we need to do is just right click and run the simulation. So EMS will automatically mesh the model and run the simulation. And also notice that the speed with which a 2D simulation is solved is extremely fast. That allows you to do a lot of 2D simulations. Earlier, when you are early in your project trying to determine the best size of your magnets or the optimal distance and so on. So 2D simulation is very, very helpful in doing a quick conceptual design. So let's look at the result table. One can get the force acting. Obviously the force acting is predominantly in the Y direction, and you can see here that's close to about 0.26 newtons is the force acting on the steel plate. And we can also take a look at the magnetic flux density. Here is the magnetic flux density due to the Hallbach array on the bottom of the Hallbach array. So you can see the high areas where high magnetic flux is there and the areas where low magnetic flux is there. Also, one can take a look at the field lines. So which is really, one can take a look at the field lines by doing the contour plot of the magnetic flux density. So this gives me the field lines emanating from the magnets due to the Hallbach array. Okay. And finally, we will do what is called as a vector plot. The same field lines, one can look at the magnetic flux as vectors to really understand how the vectors propagate. So we can go to the vector options and increase the size of these vectors. So now you can clearly see how the vectors, the magnetic flux vectors, are distributed around the model. So with this, we can actually go to our next example. Next, we will look into doing a 2D simulation of a linear actuator. Here I have a model of a linear actuator that consists of the following components. We have the copper coil, we have the cover, and then we have the armature that can move about along its axis. Now I also have the various surfaces that I will be using to do a 2D simulation that I have pre-created using SOLIDWORKS. So as before, the first step in doing a 2D analysis is to create a study. Now I select magnetostatic, and here I'm going to select an axis symmetric simulation. As you see here that this whole geometry is axis symmetric about the z-axis of the selected coordinate system. Once a study has been created, we can now apply materials to the various components. Let's select the copper part and apply material. We select the conductor material, say copper, and then apply copper to it. Then we select the air geometry and apply air to the same. Then the next two components are made of mild steel, so we apply a ferromagnetic substance to the same. Now once all the materials have been applied, the next step is to define what is known as a coil. So to define a coil, one needs to select the cross-section area through which the conductors are going to pass. It's a voltage driven coil. We have about 650 turns of M19 wire passing through this cross-section area. And the current is just, we're going to leave it as 1 amp. So once the coil is defined, we need to request the program to compute the force on the armature. With this, the definition of the problem is complete. We can quickly solve the problem and look at the results. So let's take a look at the magnetic flux density. Here is a plot of the magnetic flux density on my model. And one can easily look at the value of the force along the z-axis. In this case, it's about 0.25 newtons. So the force acting due to the current that we applied is about 0.25 newtons. Now we can do a lot of what if scenarios. What if I change the current? So to change the current, all I need to do is go ahead and change the current. So imagine from 650 turns, I have 800 turns of M19 wire. What would be the force acting? So when you make this change, you just have to rerun the simulation and you can take a look at the new result. The new force acting is going to be about 0.37 newtons. There you see straight away a jump from 0.25 newtons all the way to 0.37 newtons when I increase the number of turns. So I can take a look at the new magnetic flux density. The maximum Tesla value in the armature is about zero point 0.2 Teslas, which tells you that it's nowhere close to the saturation of the ferromagnetic steel. One can also take a look at the vector plot. Here I am looking at the vector plot. So I can increase the size of the arrows so that you can see the flux distribution in my model. And finally, we can take a look at the flux lines going through my model. So these are the flux lines. You can see the magnetic circuit and the flux lines circulating in the model. You can see most of the flux is well contained within the cover and inside the armature. So this really shows you the power of EMWorks 2D, where you can do quick simulation to understand how your designs behave. In this final example, we are going to analyze a three-phase cable. What you see here on the screen is a 3D geometry of a three-phase cable, where I have three copper conductors which are actually carrying current, and they are maintained at 10 kilovolt AC. The objective of this simulation is to do a quick 2D simulation to understand how good or how effective my insulators are. The insulator, as you can see from this geometry, are surrounding these copper conductors. As before, to do a 2D simulation, we go ahead and run the 3D to 2D converter. We select the front plane, and the program automatically computes all the surfaces that are required to do a 2D simulation. We also have the respective coordinate system, so we are ready to launch the creation of the study. So we select electrostatics simulation. It's a XY, and then we select the coordinate system. Once we select the coordinate system, we now can define the material. The outer region that you see here is air. So I'm going to apply material, and I'm going to select air, and I apply. So these are the copper conductors. So I can select them, apply material, and I open the conductor folder. Then I select copper. So the second one, I apply copper as before. And then the final one, 2, I can apply from recently applied materials. I apply copper. So the three conductors are made of copper. And finally, let's select all the insulators, and then I'm going to apply material. I open the cables folder, and I select a particular insulator with a relative permittivity of 2.37. With this, we have defined all the materials in my three-phase cable simulation. The next step now is to define the respective voltages. So let me select the first copper conductor, which is maintained at 10 kilovolts. Next, I select the next copper conductor, which is maintained at 5 kilovolts. And the last copper conductor is maintained at -5 kilovolts. So this is the worst case scenario pertaining to a three-phase voltage on which these conductors are maintained, or the maximum voltage is around 10 kilovolt. So with this, we are ready to run the simulation. Let's go ahead and run the simulation. So as you see, the 2D simulation is complete. Now we can take a look at the results. Now here is the result of the electric field distribution in this model. So you can see the worst electric field happens through the conductor or happens across the insulators, and that is what we would see in terms of the results. So it's about 3.4 million volt per meter. Luckily, our insulators have a breakdown potential of something greater than 3.4 million volt per meter. This will ensure that the insulator is okay when you apply this voltage to each of the copper conductor. Thus, it's extremely simple to actually do an electrostatic simulation to understand the electric field distribution in my model. One can also look at the potential distribution. Here you can see that the first conductor is kept at 10,000, the second conductor is kept at 5,000, and the third one is kept at minus 5,000 volts. And you can see the potential difference or the potential distribution inside your model. So an electrostatic simulation in EMWorks 2D can easily give you the electric field distribution, which will help you to understand the insulators better to see if there is going to be any breakdown, and it will also help you to study the potential difference in your model. As a quick recap, we looked at what EMWorks 2D can do. Notice that it is fully embedded inside SOLIDWORKS, and it is a 2D simulation platform where one can do both electrostatic as well as magnetostatic simulation. We looked at two examples of magnetostatic simulation. One was the Hallbach array and the other was the linear actuator. And the electrostatic simulation, we looked at a three-phase cable. And we also looked at two types of 2D simulations that are possible. We can do the axisymmetric simulation as well as the planar simulation. Notice one thing, that it is completely embedded inside SOLIDWORKS, and its look and feel is very similar to how you would use the SOLIDWORKS 3D CAD, and hence it's extremely easy to use with very small learning curve. And finally, because it is embedded inside SOLIDWORKS and because it is from the same company that gives you EMS for 3D, a powerful 3D EM simulation, you can easily graduate from a 2D simulation that can give you a quick understanding of your design to a full-fledged 3D simulation where you can look at various aspects of a model and its result in a 3D space. With this, we come to the end of this particular presentation. On behalf of EMWorks, I thank you all for attending today's webinar. To learn more about our offerings and products, please visit us at www.emworks.com. We also want to let you know that our YouTube channel, whose address is given here, has a lot of videos. Our past webinars, especially relating to our 3D product, can be accessed from this particular location. So please feel free to visit us, and if you have any further questions, we will answer that after this particular slide. So please feel free to type your questions in the chat window through your GoToMeeting, and I'll be answering them. Thank you very much.